In this video, I would like to introduce our work titled Normal Integration via Inverse Plane Fitting with Minimal Point-to-Plane Distance. So what is the normal integration problem? Say there is a surface in the 3D space. Surface normal vectors denotes the surface orientation, or they are the vectors perpendicular to the tangent planes of the surface. Now a camera observes the surface and records the normal vectors on an image plane. This image is the normal map. Given this observed normal map, the normal integration problem tries to estimate the surface that best explains the normal map. Our method is motivated by plane fitting for normal estimation from point clouds. In normal estimation problem, a set of points is given, and we try to estimate the normal vector of points, for example, at point 3. A typical way to find this normal vector is to fit a plane to nearby points of point 3. The normal vector to the plane is the one we want to find. Formally, we enforce all nearby points to satisfy this plane equation. D here is the distance of the plane to the coordinate origin, and it's also unknown. The unknown normal vector n and the plane displacement d can be found by solving this linear system. In normal integration problem, the normal vectors are given, and the points and the plane displacements are to be estimated. Here is our method for normal integration. Say there is a surface and an image plane in the camera coordinate. We have indexed the pixels from 1 to 25. Now suppose there is a normal vector at pixel 1. By back projection, pixel 1 would intersect the surface somewhere, say point 1. We locally approximate the surface near point 1 by a plane whose normal direction is from pixel 1. Then we fit the nearby points of point 1 to the plane. Here we assume closed pixels on the image plane also implies closed points in the 3D space. In this case, pixel 2 and 6 are next to pixel 1, so their corresponding points 2 and 6 should be close to point 1. We can enforce these 3 points to lie on the plane. In this way, we obtain 3 plane equations. Let's continue this plane fitting process for pixel 2. In this case, we fit point 1, 2, 3, and 7 to the plane whose normal direction is from pixel 2. We have 4 more plane equations now. We can repeat the process for all pixels that carry a normal vector. For example, for pixel and point 7, we fit its 4 neighboring points to the plane, whose normal direction is from pixel 7. By stacking all these plane equations and solving the linear system, we can solve the normal integration problem. Let's take a look at the experimental results on a synthetic normal map under orthographic projection. This normal map contains sharp features. Using traditional Poisson equation leads to Gibbs phenomenon in the estimated surface near sharp features. Our plane fitting method largely reduced this artifact. Notice that both methods find the least square approximate solutions, and there is no parameter tuning. This comparison shows that using plane fitting is more robust to sharp features. In this experiment, we gradually increase the percentage of outliers in a synthetic normal map. We can say that the surface estimated by Poisson equation is globally distorted due to outliers. On the other hand, our method largely suppresses the effect of outliers. There are local distortions, but globally, the surface is closer to the no-outlier one. In this experiment, we render a normal map for the Stanford bunny under perspective projection, then add noise and outliers to the normal map. We can say that under perspective projection, Poisson equation is likely to generate spikes when outliers exist, where there is no obvious artifacts in the estimated surface using plane fitting. The similar trend can be confirmed in a real-world normal map. This normal map is estimated by photometric stereo on a set of real-world images. We can say again, Poisson equation is likely to generate spikes when there is outliers. To summarize, we solve the normal integration problem by stacking plane equations into a linear system, and there is no parameter tuning. Yet our method is robust to sharp features or outliers in the normal map. Thank you for your attention. You can find more details in our poster or paper.